Today we are going to learn dam foundation grouting methodology and special GN method grouting in details. The process begins with drilling into the fractured foundation followed by installing the nape. Grout is injected to fill the cracks.
Hey everyone, and welcome to this explainer. Today we're diving deep into the highly technical and honestly totally fascinating world of dam foundation grouting. If you're a structural engineering student or honestly just curious about how we manage to anchor these absolute mega structures to the earth without them just washing away, well, you're in the right place. We're going to unpack the exact procedures, the methodologies, and the math that keep these massive structures standing safely for generations. So here's our roadmap for today. We'll start with dam foundation engineering challenges, then look at consolidation grouting methodology. After that, we'll compare standard versus GIN grouting and wrap up with some practical field applications.
All right, let's jump right into Section 1, Dam Foundation Engineering Challenges.
So, what exactly is our primary tool here? Consolidation grouting. Basically, it's the injection of specialized fluid grout mixtures straight into geological units. The main goal? To fill subsurface voids, consolidate loose particles, and bond rock fractures into a competent, unified mass. Think about raw earth for a second. Natural rock is almost never perfect, right? It's full of fissures, faults, and weathered zones. Simply put, this grouting process is how we engineer that unpredictable natural rock so it can actually support the immense weight and the intense hydrostatic pressure of a megastructure like a dam. Without this crucial step, even the most beautifully designed concrete dam would be fundamentally compromised by the ground beneath it.
And this process is absolutely essential. It increases the strength and stiffness of the shallow rock mass. It controls water seepage by reducing permeability, and it creates a highly uniform bearing surface for the concrete. But a really crucial takeaway here, and something you'll definitely encounter in the field, is mitigating blast damage zones. When preparing a dam foundation, the heavy blasting and massive mechanical digging required inevitably fracture and disturb the top 5 to 15 meters of rock. Think about that for a second. The very act of making room for the dam actually weakens the earth that has to support it. Crazy, right? Consolidation grouting repairs that human-made damage. It chemically stitches those microfractures back together, ensuring the rock directly beneath the dam's footprint is completely solid before a single yard of concrete is poured.
Moving right along to Section 2, Consolidation Grouting Methodology. Let's break down the exact steps we take out in the field. First up is the site assessment. By utilizing geophysical surveys and calculating the rock quality designation, or RQD, engineers can basically map out those hidden subsurface fractures. RQD gives us a hard, quantitative measure of how fractured the rock mass is, letting us know exactly what we're dealing with before we start injecting anything. Then comes Step 2, Grout Design. This is where we dial in the precise water-to-cement ratios and specific chemical additives needed for that exact rock profile. And finally, Step 3, Drilling and Injection. Out on the site, this culminates in injecting grout across a tight, systematic grid, typically spaced every 1.5 to 3 meters. That tight spacing guarantees complete overlapping coverage across the entire foundation footprint. Now, the chemistry of these grout designs is super interesting, because consolidation grouting usually targets near-surface fractures that are relatively wide. Engineers typically go for thicker mortar mixes rather than highly liquid ones. Let's consider the typical water-to-cement ratio for these thick mixes. It sits tightly between 0.5 to 1 and 7 to 1. This gives the mix a paste-like viscosity, typically flowing at over 100 seconds in a standard marsh cone test. Now, compare that to a stable, high-mobility mix. That has a much higher water-to-cement ratio, around 0.8 to 1.2 to 1, and it flows almost twice as fast, making it perfect for tight joint permeation. You can really see how tailored these solutions have to be. For those massive near-surface cavities caused by excavation, a thicker mortar is exactly what's needed to bridge the gaps without just washing away.
Once that mix is perfectly designed, getting it into the rock requires a very specific strategy. There's a brilliant contrast between downstage and upstage conventional drilling methods. Downstage drilling consolidates the ground sequentially, right from the top down. You drill a short stage, grout it, wait for it to set, and then you drill right through that new grout into the next deeper stage. This is a total game changer because it essentially builds a reinforced roof as you go, which allows engineers to use successively higher pressures deeper in the hole without worrying about the grout just blowing out and erupting at the surface. Upstage drilling, on the other hand, means drilling the entire hole down to the final depth in one single pass. Engineers insert a packer at the bottom, grout that stage, and then systematically move the packer upwards. It's often faster, but it requires the uppermost rock to already be competent enough to handle those high pressures from below.
Okay, Section 3, Standard versus Gen-G Grouting.
Historically, standard grouting was, well, a bit rigid, and it relied heavily on trial and error. It utilized strict pressure limits, which meant engineers were constantly out there tweaking variable grout mixes on the fly depending on what the rock seemed to be doing. Plus, it used traditional refusal criteria that honestly didn't always reflect the true underground reality. But then, in 1993, engineers Giovanni Lombardi and Don Dier introduced a massive paradigm shift, a much more elegant solution known as the Grouting Intensity Number, or the GIN method. The GIN method totally simplifies the chaos. It utilizes a single, stable, moderately thick grout that's governed entirely by a constant energy curve. This means you completely remove the need to constantly change mixes while the pumps are actively running.
The mathematical theory behind that curve is surprisingly simple, but incredibly effective. It's just pressure multiplied by volume equals a constant, which is our Gn. The core idea here is that the specific energy expended during injection equals the pressure applied multiplied by the cumulative volume of grout injected per meter. Think of it kind of like a budget for mechanical energy. You have a maximum amount of energy you can safely impart to the rock formation. So, if the rock is taking a huge volume of grout, you have to drop the pressure so you don't blow your energy budget. On the flip side, if the rock isn't taking much volume, you can afford to crank up the pressure. This single formula locks that critical relationship right into place.
By keeping the product of pressure and volume safely beneath that calculated GIN curve, the entire system just naturally balances itself. Let's think about the extremes for a second. In highly permeable zones where the rock is taking massive volumes of grout, the pressure is safely kept very low, and this is absolutely critical to prevent hydrofracturing. That's a super dangerous scenario where excessive pressure literally tears the rock formation apart and causes ground heave, which completely ruins your foundation. Conversely, in very tight zones where the volume is naturally low, the curve allows the injection pressure to safely build up, forcing that stable grout into those microscopic fractures. It's just an elegant, mathematically sound way to prevent both dangerous overgrouting and ineffective undergrounding.
Which brings us to Section 4, Practical Field Applications.
So how does this look in practical applications out in the field? Well, the target GIN value typically ranges between 500 and 2,500 bar liters per meter. Depending on the precise rock conditions we map during the site assessment, the ultimate hydrostatic head of the final reservoir, and the naturally occurring in-situ stress of the earth, engineers will run these very specific calculations. Setting the limit carefully somewhere between that 500 and 2,500 mark ensures that the total energy applied to the rock is perfectly optimized for that specific dam site. It's a highly customized parameter that takes pure math and safely applies it to the physical constraints of a real-world megastructure. To achieve this level of precision, engineering literature emphasizes that the application of the GIN principle entails the use of a single, moderately thick, superplasticized stable grout injected at a steady, low to moderate rate, allowing the pressure to build up gradually. You aren't shocking the system, you're gently testing the rock's capacity. But here is the absolutely critical takeaway for actual field deployment. Pulling this off safely requires real-time computer graphics right on site. Engineers have to monitor pressure, flow rate, and cumulative volume all at the exact same time to ensure the injection trajectory stays safely under that GIN curve. It is literally impossible to do this by feel or by manually reading analog gauges. It requires constant, digital oversight. Which brings us to a final thought for you to chew on. How will real-time geological monitoring reshape your next foundation design? By digitally mapping the exact energy expended beneath the earth in real time, you entirely remove the guesswork from structural engineering. You transition from just hoping the ground is solid to mathematically proving that it is. I want to leave you thinking critically about how you'll apply these advanced optimization tools to build safer, stronger, and more resilient infrastructure in your own careers. Thanks for exploring this explainer with me, and I'll catch you on the next one.